At the dawn of the 20th century, cosmology was a science confronting a crisis of scale. Astronomers had meticulously mapped the stars in our local neighborhood using techniques like parallax. But this method failed for objects beyond a few hundred light years. Beyond that limit, the universe was a flat, two-dimensional projection on the sky. Its true depth, the size of our own Milky Way, and the nature of the faint, swirling spiral nebulae were subjects of intense and unresolved speculation. This uncertainty reached its apex in 1920 in what became known as the Great Debate. On one side, astronomer Harlow Shapley argued for a single colossal galaxy, the Milky Way, stretching 300,000 light-years across. In his model, the spiral nebulae were mere gas clouds on the periphery of this grand structure. On the other side, Heber Curtis championed a universe of countless island universes, or galaxies similar to our own, arguing the nebulae were these distant systems. The debate ended in a stalemate. Both men presented compelling evidence, and both were right on some points and wrong on others. The confrontation was not merely a disagreement over facts, it was the public manifestation of a profound methodological void. The field had accumulated vast catalogs of observational data, but lacked the fundamental tool to convert them into a three-dimensional map. The impasse existed because astronomy needed a standard candle, a class of celestial objects with a known, consistent, intrinsic brightness. By comparing this known luminosity to its observed faintness, one could finally calculate its true distance. The solution to this crisis would not come from the great telescopes or the established male astronomers, but from the meticulous, under-recognized work of a woman analyzing dots on glass plates. The Harvard College Observatory at the turn of the century, under the direction of Edward C. Pickering, was less a site of quiet contemplation and more a factory for astronomical data. Pickering's ambition was to create a definitive, objective record of the entire night sky by capturing it on thousands of photographic glass plates. This industrial approach to astronomy generated an unprecedented volume of data, far more than the observatory's staff could process. To solve this problem, Pickering began hiring women to serve as computers. Their job was to perform the painstaking, repetitive labor of analyzing the plates. Paid wages as low as 25 to 30 cents an hour, these women, including figures like Williamina Fleming and Annie Jump Cannon, measured star positions and brightness, classified spectra, and cataloged their findings in dense logbooks. The system was rigidly hierarchical. Male astronomers operated the telescopes, often at remote stations like the one in Arequipa, Peru, and the glass plates were then shipped to Cambridge for the women to analyze. The computers were technicians, not formally recognized as astronomers, and their discoveries were often published under Pickering's name, with the group sometimes facing derision as Pickering's harem. Into this environment came Henrietta Swan Leavitt. Born in 1868 to a Congregational minister, she was a descendant of Puritans and carried their values of duty and diligence. She received a broad and rigorous education for a woman of her era, studying calculus, philosophy, and Greek at Oberlin College and the Society for the Collegiate Instruction of Women, which would later become Radcliffe College. An astronomy course in her senior year ignited a passion that would define her life. Her career, however, was perpetually challenged by personal hardship. She suffered from chronic illnesses that forced long absences from the observatory. Following her graduation, a severe illness left her with progressive hearing loss, eventually rendering her profoundly deaf. Her colleague, Annie Jump Cannon, was also deaf, a shared condition that may have fostered a unique working environment amidst the bustle of the observatory. Despite these obstacles, colleagues described Leavitt as possessing a nature so full of sunshine that, to her, all of life became beautiful and full of meaning. She was known to be serious, hardworking, and devoted to her family, church, and career. This patient, meticulous character was perfectly suited to the work at Harvard, where she started as an unpaid volunteer in 1895 before being officially hired in 1902. Leavitt left a faint personal trail. With no diaries and few surviving letters, her inner life is largely a mystery, reconstructed from observatory records and the memories of others. The very constraints of Leavitt's position, however, created the conditions for her breakthrough. The role of a computer was defined by its limitations: tedious work, low status, and an institutional culture under Pickering that prioritized data accumulation over theoretical speculation. This environment forced Leavitt into a deep, systematic, and purely empirical engagement with a massive, uniform dataset, thousands of plates of the same patch of sky taken over many years. While a male astronomer might have felt pressure to theorize, Leavitt's entire function was to find patterns. Her discovery was not made in spite of her restrictive role, but as a direct consequence of it. Pickering assigned Leavitt the task of identifying variable stars that change in brightness over time, within the Magellanic Clouds. These luminous patches, now known to be dwarf galaxies, are only visible from the southern hemisphere, meaning Leavitt could never see them directly with a telescope. Her entire universe was contained within the glass plates shipped from Harvard's station in Peru. Her technique was a model of scientific rigor. To find variables, she would place a negative plate over a positive contact print of another plate taken on a different night. A star of constant brightness would appear as a neutral gray dot, its positive and negative images canceling each other out. But a variable star, having changed in brightness between the two exposures, would betray itself with a distinct black or white halo. She also employed a device called a blink comparator, which rapidly alternated between two plates, causing any star that had changed brightness to appear to flash. Once a variable was identified, she would meticulously measure the diameter of its photographic image on plate after plate, using the size as a proxy for its magnitude, and record the data in her logbooks. Through this process, she discovered over 24,000 variable stars, about half of all those known by 1930. The first public hint of her monumental discovery appeared in a 1908 Observatory publication. After cataloging nearly 1,800 variables, she singled out 16 specific stars of a class known as Cepheids and made a characteristically understated remark. It is worthy of notice that the brighter variables have the longer periods. Leavitt recognized that the Magellanic Clouds offered a unique, controlled experiment. She reasoned that all the stars within one of the clouds must be at roughly the same distance from Earth. This assumption was the key that unlocked the problem. It meant that any observed difference in the apparent brightness of two Cepheids in the small Magellanic Cloud must reflect a true difference in their intrinsic luminosity. For the first time, the relationship between a star's period and its luminosity could be studied without the confounding variable of distance. She pursued this relationship for 4 more years. In 1912, in a paper published in the Harvard College Observatory Circular, communicated by Pickering but with the opening line noting it was prepared by Miss Leavitt, she presented her definitive findings for 25 Cepheids in the SMC. Plotting the stars' brightness against the logarithm of their pulsation period, she demonstrated a clear linear relationship. As she wrote, "A straight line can be readily drawn among each of the two series of points, thus showing that there is a simple relation between the brightness of the Cepheid variables and their periods." This relationship, now known as the period luminosity relation or Leavitt's law, was the cosmic yardstick astronomers had been searching for. It transformed Cepheid variables into the first reliable standard candles. An astronomer anywhere in the world needed only to measure a Cepheid's period, the time it took to complete its pulse, to deduce its true absolute brightness from Leavitt's graph. By comparing that absolute brightness to its apparent brightness in the sky, its distance could be calculated with the inverse square law. The remarkable accuracy of her work, conducted by eye with a magnifying loupe, is evident when compared to modern measurements. Leavitt's law did not just contribute to cosmology, it acted as a causality engine, setting off a rapid and direct chain reaction of paradigm-shifting discoveries. The first domino fell at the Mount Wilson Observatory in California. Armed with Leavitt's discovery, astronomer Edwin Hubble pointed the world's most powerful instrument, the 100-inch Hooker telescope, at the Andromeda Nebula. On a photographic plate from the night of October the 5th and 6th, 1923, he marked a faint star he suspected was a nova. Upon checking previous plates, he realized it was varying in brightness. This was a Cepheid variable. Hubble meticulously measured its period at 31.4 days and its average apparent magnitude. Applying Leavitt's law, he calculated its distance to be roughly 900,000 light-years. Even with Shapley's generous 300,000 light-year estimate for the Milky Way, this result was unambiguous. Andromeda was not a local gas cloud, but a colossal independent galaxy, an island universe far outside our own. With a single calculation based on Leavitt's work, the great debate was settled, and the known universe expanded immeasurably overnight. He continued using Leavitt's yardstick to measure the distances to more and more galaxies. In 1929, he combined these distances with redshift measurements made by Vesto Slipher, which indicated the galaxy's velocities. The result was his second monumental discovery, a direct correlation between a galaxy's distance and its recession speed. The farther away a galaxy was, the faster it was moving away from us. This relationship, Hubble's law, provided the first observational evidence for the expansion of the universe and became the cornerstone of the Big Bang theory.